The LANDFIRE mapping team works behind the scenes to produce disturbance products from the most current imagery and data available. In this video, we'll unveil how LANDFIRE disturbance products are created by highlighting the key aspects along the way. But first, what constitutes a LANDFIRE disturbance? LANDFIRE calls any landscape change, whether human or natural caused, a disturbance. Examples might include wildfires, timber harvests, herbicide treatments, insect invasions, or natural disasters. With so many changes occurring on the landscape each year, it's no wonder our disturbance mappers are hard at work behind the scenes. LANDFIRE disturbance mapping begins with the generation of high-quality satellite imagery from harmonized Landsat and Sentinel data. These satellite image composites include thousands of individual satellite images and serve as the foundation for creating out-of-the-box change detection products. So how does LANDFIRE transform satellite images into usable LANDFIRE products? The following stepwise procedure happens each year and has recently been improved. The simplified version starts with the compilation of satellite imagery. Then we organize event data. This means that any agency that has polygons delineating disturbance data or events are provided to LANDFIRE and organized by our team. Next, we run our automated tools. We'll explain those later. And finally, LANDFIRE mappers review and check their work and deliver the final disturbance products. So let's talk about the inputs that go into building these LANDFIRE disturbance products. Some examples include the spatially adaptable filter for error reduction, or SAFER. Check out the link in the description to a 2024 paper that describes this one further. One you'll hear me refer to often called MICA, or the Multi-Indexed Integrated Change Analysis. Built from image composites, MICA is a key dataset used often by disturbance mappers to pinpoint disturbed areas. You can learn more about MICA in the description below as well. The differenced normalized burn ratio and the normalized difference vegetation index. These are important for detecting change in both public and private lands. In addition to satellite-based change detection, submitted event polygon data discussed previously and fire program data such as MTBS, BAER, and RAVG are all used to generate LANDFIRE disturbance products. In short, all the data listed are processed through a series of automated scripts designed to help distinguish genuine land cover alterations from seasonal greenup or annual variations linked to rainfall and weather patterns. These automations greatly reduce the manual effort required for identifying actual disturbances. So what's a day in the life of a LANDFIRE disturbance mapper actually like? Let's take a look. In this example from Missouri, the red, yellow, and orange pixels represent MICA data, and the brown pixels represent SAFER data, both of which are detecting a disturbance. By toggling on and off the 2022 and 2023 imagery, we can see the 2022 circled landscape is green, signifying an intact vegetation canopy. In 2023, there's a slight transition to brown, indicating a reduction in vegetation cover. Most likely, there was a thinning or selective harvest in this patch of forest. Since the automated change products don't adequately capture the complete disturbance boundary, the mapping analyst will manually draw in the disturbance boundary using editing tools in ArcPro. In the end, this disturbance is labeled as unknown because it was detected by our automated change detection scripts, and no disturbance event polygon or data was provided by the local manager. Therefore, it cannot definitively be assigned to a specific disturbance type or treatment activity. For the second example, we're looking at an area in the Midwest. The clusters of pixels from the various change products indicate some sort of disturbance has occurred. Because multiple data sets are homing in on this one spot, the disturbance mapper can be confident that the disturbance picked up by the automated scripts are truly representative of an actual disturbance. High-resolution imagery, when available in Google Earth, is sometimes used to help verify whether or not a disturbance is valid. Here we can see in higher resolution where land has been cleared for a newly intended purpose. In cases like this, where the change products accurately define a disturbance boundary, the analyst draws a rough outline around the disturbed pixels, which indicates their validity and signals that they should be retained as a disturbance. Once again, the disturbance remains unknown though, because no event data or polygon was provided to LANDFIRE. If users are familiar with the landscape or aware of recent disturbance activities, unknown disturbances can be updated to a more appropriate class by recoding the data using any GIS software. To learn more about this process, contact the LANDFIRE Help Desk at the address in the description below. In the third example, we'll zoom over to Oregon, where we can get an idea of what a typical Western disturbance looks like. We can see from the blue DNBR data, the brown SAFER data, and the red, orange, and yellow mica data that something occurred here. Toggling between 2022 and 2023 imagery confirms what the change products detected. For the purpose of this tutorial, we'll check out Google Earth to see the disturbance in high resolution, and looking closer, the disturbance mapper can detect on multiple tracts of land that these were clear cuts. In conclusion, we can see the disturbance event boundaries from 2022 here in purple and in red for 2023. But again, because LANDFIRE wasn't provided with any disturbance event polygon data, the disturbance remains classified as unknown, despite what we can see on Google Earth. But updating unknown disturbances can be done by recoding the data using any GIS software. Just north of this disturbance event, we see an example of why submitted disturbance event polygon data is so important to LANDFIRE. Some disturbance events are readily detected by our change products, as in the previous examples, but many are not. These tend to be smaller in size. For example, they might be treatment activities such as herbicide or insecticide applications. Here we're toggling between 2022 and 2023 imagery, yet our change products are not picking up anything. But because multiple disturbance event polygons were submitted to the FACTS website and then provided to LANDFIRE, we know that along this road there is an herbicide application, and this disturbed polygon represents a thinning event. These disturbance event polygons are key to having a complete picture of what's changing on the ground. To maintain high product standards, the disturbance mapping team works together to review each other's intermediate disturbance products. For example, once a mapper finishes processing a tile, they put it in the queue to be checked by another team member. This review process ensures data consistency and quality. Following the check, the intermediate disturbance product is passed through a final layer of automated checks and balances to ensure all expected data are present, values and pixel counts match, and the source data match the final product. After those final scripts are run, the disturbance layer is ready to be delivered to our end user. Do you want your local disturbance data included in LANDFIRE's disturbance products? The LANDFIRE team is hoping your answer is yes. To submit this disturbance information, please visit landfire.gov and find the Contribute Data section. Submitting your local disturbance boundaries and information matters because when natural resource professionals record and upload their local disturbance event boundaries to partners of record databases or send them to LANDFIRE directly, our disturbance team can more accurately map and track disturbances on the landscape, which has significant impacts for other LANDFIRE products. In the next video, we'll break down the differences in the 3 LANDFIRE disturbance products being released throughout 2024.